Hello friends. In continuation of the Compton scattering experiment, now I want to tell you how the experiment is actually done. Okay. So let me first revise a little bit about the GM counter. Now what is the Geiger-Müller counter that we use to measure intensities in our experiment? It works on the basic principle of photoelectric effect. Okay. So you have a steel tube, and whenever a high energy electron or a high energy photon, sorry, is incident on one end of it, you will have some photoelectric effect. Or if it does not interact with the metal atoms here, it goes in, it is filled with a dilute gas, so it ionizes one of the gas atoms. Okay, either way, either by photoelectric effect or by ionization, a single electron is generated at one end of the detector, and a potential of about 500 volts is present across the detector, which accelerates this electron. Now remember that an X-ray is a very high energy photon, so the initial energy of any emitted electron is also fairly high. So the electron is already moving with a high momentum and you are now accelerating it. So along the path, the electron is going to ionize other atoms, and those electrons subsequently ionize even more atoms, and eventually you have what is called an avalanche effect. Okay, and ultimately at the other end of the detector, if you measure the current, okay, there is going to be a pulse of current. This is time and this is current, and the pulse of current gives you a measure of how many electrons in that time frame got ionized. Okay, and by doing a sort of back calculation, you can tell how many incident photons were there. So in this sense, the back calculation is of course, beyond the scope of this discussion, because that is called the calibration of the detector, which needs to be done with utmost care. But no matter what, we can resolve the number of incident photons that are incident on the detector, but we cannot measure the energy of each photon. Okay, so that is the big problem when it comes to the Compton scattering experiment, because we have to measure lambda. We have to measure lambda prime, which is the scattered wavelength after Compton scattering, and we have to measure lambda naught, which is the incident wavelength before Compton scattering, and we have to measure we have to measure the difference between these two. And how are we going to do this when we don't have a detector which can measure the energy? So for this part, we use a result that we derived, or rather that we measured in the last part of the X-ray diffraction experiment, which is that of photon absorption. Okay. So just to revise, if you have a thin film of aluminium, we use aluminium, you shine some intensity I naught, and what comes out of this side is I, and I by I naught is empirically known to be exponential minus mu t, where t is the thickness of this, uh, thin film. Okay, now mu is called the photoabsorption coefficient, and or X-ray absorption coefficient in this case, and it's usually a function of lambda. Okay, so if we know mu as a function of lambda, or in other words, if we fix t, if we know I by I naught as a function of lambda, okay, if we have a plot of the transmission coefficient and lambda. And transmission coefficient is something that we can measure using our detector because it's a ratio of intensities, and that is exactly what we measure using Geiger-Müller counters. Then, and if we know this function, say if it is roughly linear, then by reading out lambda, by measuring the transmission coefficient, we can have a lookup table between the transmission coefficient and the lambda if we know this nearly linear behavior around a certain, in a small region. Okay, so this is the principle that we use to actually measure the wavelength in the Compton experiment. So we do the photon absorption, X-ray absorption experiment, and we fit the transmission coefficient to a linear function of lambda, and then use that to measure the lambda by measuring the transmission coefficient. So we don't directly measure lambda, we directly measure the transmission coefficient and infer lambda from that. Okay, and now that is one part of the experiment. And for the Compton scattering itself, we use an acrylic glass slab. Now, why is acrylic glass slab used in this experiment? Now, acrylic, so if you remember the theory behind Compton scattering, it involves free electrons. Acrylic glass is an insulator. Now, why are we using an acrylic glass slab at all? The reason for that is not so much because acrylic glass slab has a lot of free electrons, but a very strong signal that competes with Compton scattering, which is usually a much weaker signal, is that of X-ray diffraction. So if you use a crystalline substrate, you will see a very strong signal of X-ray diffraction, which masks the Compton scattering. And especially since you are using intensity measurements to ascertain the wavelength in the Compton experiment, you don't want very strong intensities coming at specific angles due to X-ray diffraction. So we need to use a non-crystalline substrate. So even though acrylic glass doesn't have a large free electron density, we will use acrylic glass in this experiment so that it's an amorphous, or it's a glass. So it is not a crystalline substrate. So it doesn't have any X-ray diffraction signal. And whatever signal that you receive is primarily due to Compton scattering. Okay, thank you.